Howdy folks, welcome back to another CS 128 Honors Lecture. Today we're going to be covering borrowing and slices in Rust. So we're going to start off by answering a bunch of your questions. Thank you for sending those in, and the homeworks and the MPs. We do read your responses to the free response questions in PrairieLearn, so keep sending in any questions you have, any comments, whatever it may be. We will answer those questions in today's lecture and in future lectures. Then we're also going to review some ownership and borrowing again, and then talk about dereferencing mutable references, something that will be helpful in homework 3 and homework 4. And then we're going to talk about slices of strings and vectors. And at the end, we're going to review MP0, talk about some common approaches, and then some of the optimal solutions that we were looking for. Just a couple quick reminders before we get started. Homework 5 is releasing tonight. It's due on the 23rd at midnight. Homework 4 is due on the 17th at midnight. And MP1 is due on the 23rd at also at midnight. All right, let's get into questions. So we know ownership is tough. We will be going over it because it is such a central concept to Rust. Everything we're going to cover in future lectures will be taught through this lens of ownership. And so that's going to be structs, multi-threading, functional programming, iterators. They all have some sort of variation of ownership, and we'll be covering these concepts, sort of seeing how ownership affects these topics and how it causes these nuances that Rust has. Next question. So when we use enums in a match statement for a variable, how does this variable have to be an enum type 2? So short answer, no. Let's get into a quick example of this. So I have this variable, my result. My result is a enum. It's a result enum. So we're matching this variable, my result. But in our enum variants here, we have an enum variant OK with a number contained inside of it. And so this variable here, num, does not have to be an enum. Num, in this case, as you can see, is an I32. And so we can extract that num using our match statement, compute some calculations upon it, and print it out at the end. And so when we're matching, we can match an enum or any other type. And in our variants, we can have variables inside of them. But these do not have to be enums. They can be, but not necessarily. So go ahead and run this. So at the beginning, we're getting some results OK, extracting that value and adding 10 to it. So we got 138. Down here, we're getting some arbitrary error. And so we enter this error branch here and printing out that message. And so there's another question coming up talking about sort of this bracket notation with either the empty brackets or with a colon and a question mark. In short, empty brackets is pretty printing, and colon question mark is debug printing. It's a bit more nuanced. Get into that in just a bit. Okay. So, like I said, debug printing is colon question mark, and pretty printing is just the empty brackets. General rule of thumb, use the empty brackets for primitive types, so integers, floats, booleans, characters, and for strings. And then use the colon question mark debug printing for custom types. So this includes vectors, any other data structures like hash maps, hash sets, trees, heaps, whatever it may be, any other custom types that you may create. So that can be structs, enums, anything along those lines. It is a little bit more complicated on when you can use the pretty printing style. It honestly depends on the specific implementation of each type. We'll get more into this when we get into traits towards the end of the semester. But yeah, in general, colon question mark is used for debugging, and empty brackets is used for pretty printing. Okay, so we didn't have enough time to cover dereferencing in the last lecture, but dereferencing is essentially accessing the data that the reference refers to and changing it, if you would like to. So this is very similar to C++ syntactically. You put a star in front of your reference, and then you can complete any operation you'd like upon that dereferenced value. So let's get an example and see what this looks like. So again, if you're following along, you can pull up the lecture 7 folder in the lecture code. Okay, so we have this mutable integer here, and we're going to pass a mutable reference into this deref_int function. And so deref_int will take that mutable reference, dereference it, and add 4 to it. And so in dereferencing this number, we have access to the data contained inside the reference, the data that this reference refers to. And so now that we have that piece of data, we can modify it however we like. So run this real quick. And so here before the deref, we have 124. And after the deref, after we add 4 to it, we have 128. So let's move on to the strings. So at the start, we have this string hello. And we're going to pass into this deref string function, pass in a mutable reference to the string. And in deref string, we are dereferencing s with the star operator and changing the data contained, changing the data that the reference points to. So we're going to reassign this reference to goodbye. And so you can see that in the results. Before our dereference function call, the string is hello. We print that out. And after, the string is goodbye. And so to get access to the data inside a mutable reference, you have to dereference that. Okay. And so I want to show you just a quick example, a look ahead into structs. And so you'll notice that we don't need a dereference when calling methods upon s that will modify them. And so this sort of goes into ownership and structs, which Eustace will cover briefly in the next lecture, and we'll get more into structs next week. But here you can see we're not dereferencing s, but we're modifying the data that it's pointing to. In short, s owns itself, and so s can mutably mutate itself without having to dereference itself. Yeah, more on that in the next lecture. Okay. So there is a little bit of a confusion between the capital S string and &str. So in short, &str is a reference to a string literal or a slice of the string. So we were sort of hiding a little bit because we had not introduced borrowing yet. We'll go much more in depth into &str slices in this lecture in just a little bit. In short, &str is a string literal. It's a reference type. String, capital S, is a custom type, and it has ownership over its characters. So in this example, this let ref is essentially a pointer to this string data inside this memory stack. So when your program starts up, it's assigned this sort of piece of memory inside your RAM. And so that piece of memory is partitioned into a bunch of different parts. You'll learn more about this in CS225, CS233, and those future classes. But anyways, this string literal is built into your program code. And so your string literal will be stored inside this initialized data section. And so ref is actually a reference to that piece of data inside the initialized data. On the other hand, when you create this variable string is a variable in the stack, so it's located up here, but its characters, so testing 1, 2, 3, those are stored on the heap. So you have a pointer from the stack, the string, and it owns the characters on the heap. Again, you'll cover more about stack and heap semantics in future classes, but &str, the slice type, is a reference to some piece of data somewhere. Okay. Before we get into slices, I just want to review the 3 rules of ownership briefly. So each value in Rust has a variable called its owner. There can only be one owner at a time, and when the owner goes out of scope, the value will be dropped. So you saw this example in the last lecture, but S owns this piece of data hello, and S comes into scope on this line, and then we enter a new block of scope. W comes into scope here, W owns world, and at the end of this block of scope, W is dropped. And then finally, at the end of main, S is dropped. Then, again, there can only be one owner, so when you try to reassign a variable, so let y equals x, y will now have ownership over this string data hello. And so you will not be able to print out x, but you can print out y. And then a quick review of references. The ampersand represents a reference type. You can refer to some value, but you're not taking ownership of it. And so the act of creating a reference is called borrowing. And so when you borrow, you can have either one mutable reference at a time, or you can have an infinite number of immutable references. You use the ampersand for an immutable reference, and the ampersand mute operator for a mutable reference. So again, either one mutable reference or an infinite number of immutable references. Not both, not a combination, one or the other. And so in this case, we're creating a mutable reference to x, and so y is the only single mutable reference in this program. And so that means we cannot create a mutable reference when we try to push to x. More on this when we cover structs with Eustace and the next weeks. But again, one mutable reference or an infinite number of immutable references. Okay, on to string slices. So I want to reiterate this again. The string type has ownership over its characters. It has its characters somewhere in memory, somewhere on the heap, and the string type owns that array of characters. But if we wanted to take a substring, we can take what's known as a slice. A slice is a reference to a portion of that string data, a portion of that array of characters. And so the original string will still have ownership over those characters. It's just this slice type will be a reference to that data in memory. And so let's say we have this string s1, hello, and so on the stack, this is somewhat simplified version of what a string looks like. We have a pointer to some array of characters on the heap, and the length of the string, and maybe a capacity variable. So this s1 owns these characters hello, and we can take a slice of it. So we can take a sort of reference to a portion of the string if we'd like. So let's see what that looks like. So when we want to create slices, we're essentially creating a reference to a portion of the string. So we use the ampersand symbol again to create a immutable borrow of the string. And then we need to specify a range, the number of characters we want, and sort of where we want to start and where we want to end. And so you can do that with a couple different types of notations. You can use the brackets with an index to start at and an index to stop at. So the start will be inclusive, stop is exclusive. Or you can not specify a starting index, just go to some end. And so if you don't specify a start, Rust will assume that you mean start at index 0, inclusive, and stop, exclusive at stop. You can also do the same, the opposite actually. You can start at some index and go to the end, and Rust will assume that you want to end at the end of the string. Finally, if you want to make a slice of the entire string, effectively a borrow, you can just put bracket dot dot bracket. So this is the same as just borrowing the string with ampersand. And so because we're using the ampersand operator, slices are read-only, they're immutable. You cannot change the characters that you have access to with a slice. So we had this string s, hello world. We have the hello variable pointing to the characters hello. So we start at index 0 and at index 5 exclusive. So 0h, 1e, 2l, 3l, 4o, and we ignore 5 because it's exclusive. I want to note that this is the same thing as not specifying 0, so just dot dot 5. They are the exact same, syntactically, just syntactically different. And then world start at 6, end at 11. You'll notice that this string is 11 characters long, and so ending at 11, the length of the string, 11 is exclusive. And so we'll actually use the character index 10, D, and nothing after it. And so this is the exact same as just specifying the starting index 6 and going to the end. Finally, this little hello world, this entire string, specifying bracket dot dot bracket is the exact same as if you did not have the brackets at all. So ampersand s is the same thing as creating a slice of the entire string. And I want to note, these slices are read-only. You will not be able to change the characters using this variable hello and world. You won't be able to change s in this case because it's not mutable. So just something to keep an eye out for. So I want to sort of cover what slices are under the hood to give you an idea of what you're working with. So in this example, we have this string s pointing to this data hello world. And so in memory, we have this, this struct on the stack. Struct contains a pointer to some array of characters, the length of our array, and a capacity. And so in memory, we have this array with all of these characters. And then when we try to create a slice, we are essentially creating a pointer, a reference to this piece of data. And so under the hood, our slice might look like this, just simply a pointer to some place in memory and the length of our slice. And so if we want to start at index 6 and end at index 11, we have a slice of length 5, and our pointer will point to the start of our slice. So index 6, and that's the W character. So you might notice that string literals and string slices have the same type. They're both ampersand string or ampersand str, but they are somewhat different. A slice has to be constructed from a string, as you saw before. You have to sort of take a reference of a capital S string, but string literals don't really refer to a capital S string. They're just literally some quotes and some text in between them. Well, that's because the string literals are actually baked into your program code. So when you're when you're starting up your process, starting up your executable, these characters are built into the code. So they are initialized in this initialized data part of memory. So on startup, they're loaded into this section of your RAM. And so when you're creating a string literal, you're effectively creating a slice of this initialized data. So in this case, I have my slice world, and it contains a pointer to some place in this initialized data. And we only want to read 5 characters, 5 bytes, so we know where to stop reading from memory. And so in essence, string literals and string slices are very, very similar in that they just contain a pointer to some piece of data somewhere in memory and the length of how far to read. So it doesn't matter where you're taking the slice from, it just matters that you have a pointer reference to some piece of data and you're looking at how much to read from that reference. And so again, I want to reiterate, when you're taking slices, you're taking sort of a reference to this string. And so in memory, S and world, well, these would live on the stack because they're stack variables. And this pointer would most likely refer to some data on the heap. So this entire character array would live in the heap here. And so your string slice world in this case refers to some data on the heap, as compared to your string literal, which refers to some data in the initialized data section of memory that's loaded on the start of your program. So you'll cover more about this when you cover computer architecture, systems programming, and that sort of stuff when you really look at memory in depth. But I want to give you guys a quick look ahead. All right, let's get into an example of slices. So again, following along, you can look up slice.rs in the lecture code. So I have this slice hello world, and I'm taking a slice from 0 to 5. I can remove the 0, and it will have the same functionality. So I can run this. And so our code should print out hello, and then world, and then hello world, because we're taking a slice from 0 to index 5, HELLO, and then another slice from 6 to 11, WORLD, and then finally a slice from start to finish. So I can remove the end index here, and then I can specify, or rather, remove this entire bracket notation. And so this should print out the exact same thing. And there you go. Hello world and hello world. So we can also take slices of vectors. We have our sort of vector of integers, an array of integers in memory, and we can take a subset of that. So you might be familiar with the array notation. Well, we're taking a borrow to an array. A reference of an array is the same thing as creating a slice of a vector or a slice of an array. And it's the exact same notation. You borrow your vector with the ampersand operator and then use the bracket notation to take a slice of that. And so my slice will be 1, 2, 8, because we're taking 0, 1, and 2 indices of this vector and excluding 3. And so when we print this out, we'll be printing out 1, 2, 8, as you saw right here. And we can, again, take a slice directly in our loop, take values 2, 3, and 4, exclude 5, and print those out. So run this again. So we have 1, 2, 8 because we took indices 0, 1, and 2, and we have 8, 1, 9 because we took indices 2, 3, and 4. So slices are syntactically exactly the same as taking string slices, except vector slices are borrows of arrays. You'll cover this in 225, but vectors are in essence a resizing array. You have some array of values on the heap, and your vector class will change the size for you. That is a little bit of an advanced feature, but something to look out for. So just to reiterate, vector slices are constructed the exact same way as a string slice. You borrow the original vector, and you specify a range with a start ... stop notation. And again, slices are read-only. They are immutable. You're borrowing immutably, so you cannot change the data inside your slice. All right, that is all the new content for today. I want to take some time to review MP0. So pull this up. So we were sort of looking for a couple of things in this MP. Biggest thing was learning how to use the match statement. So you can match a character, and you have to specify all the options you want to sort of match, and then a wildcard operator for sort of things that you do not want to match. So in this case, extra credit if, well, not extra credit, but kudos if you were able to figure out you can use this bar operator to put two values on one line if they have the same outcome. And then one more thing, just figuring out how to use enums. Most of you were able to figure that out. You can wrap the result in a sum when you want to return an option, or just specify none. Okay. Another sort of advanced solution we were looking for is this tuple destructuring. So getEquation tuple is going to return a tuple of options. And so you can get that two values separately using this tuple destructuring notation. So let, in parentheses, x comma y gets you x to refer to this first option and y to refer to the second option. And then immediately, if this parsing fails, x is none or y is none, you return error. So looking for the is none method here. You could also use a match statement. You could match both x and match y and return an error if either of them were none. Next, we are sort of looking how you can handle parsing a float. So parse F32 will return a result type. And so this is what we're looking for when we kind of match results, very similar to matching options, except error will have this sort of variable in here. And so matching both the x and y is very, very similar. Another sort of sneaky test case we added in is sometimes these options might have extra spaces in them. So you'd have to trim the extra white space surrounding the sort of number content if you'd like to parse it cleanly. And again, we're able to use unwrap because we know 100% x and y are both not none at this point. So we can unwrap them safely without our program crashing. So this was a sort of tricky bit here, finding the operation in your equation. And so the optimal solution we're looking for is using this operation from char function that you guys created earlier. So effectively, we're going to iterate through all of the characters in our line and try and match that character to an operation. And if we are able to, then we've found an operation. We've found a number or a operation that we can safely return and continue on with the function. And so we have this mutable option operation, and we started as none. And so we don't have null values in Rust, and there's no sort of null value in our operation enum. And so we can specify some null value, something that means nothing, with an option type. And so this is another amazing use of the option type in Rust. And so as you go through these characters, if you find that the return type of your from char function is some, then we can reassign this and even break at the end. And then finally, you return this result type OK with num1 and num2, and then you unwrap your option because you know that you found it. All right, and the solve function, again, some more tuple destructuring. You know that parse equation returns a tuple, and so this value contained inside OK is going to be a tuple. You can destructure that and assign that to another tuple destructuring here to match A to num A, B to num B, and O to op. And finally, another match statement. You're matching your operation and executing the correct operation based off of the enum you see. Finally, the solve all function given a file path, and this is some more matching, checking whether you can open the file and handling that error correctly, and then using this buffered reader to get the lines of your file, finally using a match statement within this logic. And so a really, really sort of compact and clean solution is to use two nested match statements. So you match the line because line is of result type. And so if line is OK, you try and solve the line. Another approach would be to match the line, extract the line from it, and then in a separate match statement underneath, you'd call this solve function. So both approaches work. There are multiple ways to solve all of these functions in the MP. Just we're showing you sort of a TA solution. And so if you are able to match the line, if line is OK and solve is OK, you had a valid equation, we increment result with n. And if for some reason we error it out, if we could not solve the equation or we could not unwrap line, you can either add 0 or do nothing with the unit type notation. This expression will return nothing, and so you would do nothing. It is equivalent to just adding 0 to results. And at the end, you pass in this result to an OK enum variant. All right, that's all, folks. Thanks for watching, and I will see you guys next week for another lecture. Eustace will be covering structs on Thursday, so keep an eye out for that lecture. Take care.